All right, everybody. This is the last worksheet of the unit and the year for this weird year. And we're going to practice recognizing asymptotes on a graph. Now, we're not actually going to graph anything, because chances are if you use this in the real world, you'll have Desmos graph it for you. But we've got a list of equations, and we also have a list of graphs. So what we're going to do instead is play matching. Can you figure out what finding horizontal, vertical, other things, what does that mean? What might it look like? So what do we look at first when we start playing matching? The easiest place, in my opinion, and at this point we're kind of going with, here's what I would do. There's not really a right way or a wrong way to do this as long as you're using correct techniques. I would look for horizontal and oblique asymptotes because you don't have to take the fraction apart. And you can see them right on the fraction. What they're going to look like on a graph, okay? On some graphs, you'll find a dotted line, and that will indicate a horizontal asymptote. Usually you don't get them for slant or oblique asymptotes, but some graphs, some don't, but some graphs will give you the dotted line. If it doesn't give you a dotted line, look at end behavior on the far left and the far right. So this first graph, when I talk about end behavior, try and get away from any of the vertical asymptotes, okay? So as we get really far away, you can tell this isn't slanting, it's leveling off. It's harder to tell on the right side, because on the right side, you're like, oh, well, maybe it levels off at -1, but see how close it is to the vertical asymptote? That's too close. But if you can get something that's further away from that vertical asymptote, it's a little bit easier to tell what it's doing, okay? So horizontal and oblique asymptotes are the easiest places to start, in my opinion, okay? So you can just kind of scan through, and you don't have to tear fractions apart. Okay, now what if those don't work? What else can you look for? Okay, the next place you start looking is you're going to be looking for excluded values. Okay, now excluded values, they're also called discontinuities. Those are your holes and your vertical asymptotes. Okay, holes and vertical asymptotes. Those are things that interrupt the graph in the middle of nowhere. Okay, in order to find them, you frequently have to factor. Okay, they're found in the denominator, and as far as, what do they look like on the graph? Your horizontal and oblique asymptotes, the numbers you get are indicating y values, or the height. The numbers you get for holes and vertical asymptotes, those are x values, because especially the vertical asymptotes, they kind of tunnel through an x. And oftentimes you get a dotted line again. You don't always get a dotted line, so if you don't get a dotted line, look for where the graph sweeps up and then down on the other side. Okay? But it's the dotted line, and it's an x value. That's your vertical asymptote. Now, holes, if the graph shows you holes, they don't always, but if it's going to show you a hole, it looks quite literally like a hole. That's the hole. Holes are really easy to spot, okay? The way you can tell what a hole can be canceled. Okay, so if you come across a hole, it's something that is in the denominator, it's involving an x, and it can be canceled. Vertical asymptotes come from x's in the denominator, but they do not cancel, okay? All right, so going back to our originally starting place, horizontal and oblique asymptotes. The way you tell the difference, horizontal asymptotes, you're looking for your highest degree. Okay, if your highest degree is on the bottom, that's a horizontal asymptote. If your highest degree is tied top and bottom, that's also a horizontal asymptote. And the numbers you get, if it's just on the bottom, you get 0 because you just bottomed out. Or if it's tied, it's whatever numbers are in front of the tie. The oblique asymptotes, the only time you get those is when your highest degree is on top. That's the only time those happen. All right, so let's give this a shot. We're going to look for highest degrees, and they are tied. That means it is a horizontal asymptote. And the value for it is whatever's in front of the tie. Okay, so we've got this horizontal asymptote, and it's something over 2. The 2 has to stay on the bottom. But you need something on top, because that just looks weird. It's like a repeating 2, but there's only 1. That's weird. So hidden ones, they show up somewhat frequently. Okay, highest degree. We're looking at top and bottom again. And this looks really similar to the last problem. Okay, so we're looking for whatever's in front of the tie, and it appears to be, once again, a 1/2. Okay, down here, we've got the highest degree on top. Okay, if your highest degree is on top, it's flying away from you. That is a slant asymptote. This thing slants. Now, if you're just playing matching, we're not going to actually long divide this and find out what the line is, because sometimes that's really hard to tell on a graph because there's generally no dotted line for a slant asymptote. Okay. Last but certainly not least, we have a bottom dwelling high degree, which means that this thing is a 0 for a horizontal asymptote because it just bottomed out. Okay, it bottomed out at 0. So we've got 1 slant, a horizontal at 0, and then 2 horizontals at 1/2. So on that information alone, let's see if we can figure out what graph might match. I'm over at the B graph because it was the first one the camera focused on. Okay, going across, that's a horizontal asymptote, and it's crossing the y at 1/2. So that's one of our first 2 equations. Let's look up here at A. What's going on at end behavior? Because I don't see any horizontal lines. So on the ends, what's going on? That sure looks like it's leveling off. That doesn't look like it's slanting. And there's also something on these, if you look really closely, there's like tiny little arrows that don't go off the grid. They're at the end of the grid before the line goes off the grid. That's actually a horizontal asymptote indicator, and it goes through the y's 0. So if you can look at those, they're really small, and they're kind of hard to see, but that's what they mean. Okay, so they're at the very edge of the grid. They don't go off the grid. They just go to the edge of the grid. Okay, here's a horizontal line. It crosses through 1/2 at the y. So that is a horizontal asymptote at 1/2. Okay, and this guy, as it's going to its end behavior, so not the middle stuff, just the end stuff, that's slanting. And it's not converging on the same point. One side's going up, the other side's going down. They're not horizontally going to the same point or the same number. So that's a slant. Okay, so that was D. We know D slant, so I'm going to fill that in right now. So notice I haven't even touched the denominator. I haven't factored. A lot of this you can figure out just from horizontal and oblique asymptotes. Okay, we also know that one of our functions does bottom out. Okay, it bottoms out. It's too heavy on the bottom. It's dragging along the x-axis. That's the A. So we know that this bottom guy, as I try and keep the pen from hitting the camera, is an A. So we've got half of the problems already figured out, and we haven't done any factoring. Okay, last, but certainly not least, these 2 unfortunately have the same horizontal asymptotes. So we're going to have to do a little bit more work to figure out which graph they belong to. Okay, so looking back, let's look for excluded values. Okay, this is going to involve some factoring. Now, the first thing I'm going to do is I'm going to factor the denominators. I'm not going to worry about whether it's a whole or a vertical asymptote, because sometimes you can actually avoid that too. Now, see how on the bottom, everything has something that can be divided by 2 in front? that's a greatest common factor. Pull out a 2. Let's see what it looks like when we do that. So x squared plus 2x minus 3. Okay, need to factor that. Oh, but look here, while we're grabbing greatest common factors, the guy below it has almost the same setup. We can pull a 2 out of that, and we get x squared plus x minus 2. All right, and now we can do kind of all of our factoring at once. So they have slightly different polynomials down there. So they're going to have different excluded values, and that should really help us out. Okay, so in the top equation, we need things that can multiply to 3, but then they have to subtract to 2. Oh, 3 and 1, multiply to 3 and subtract to 2. So that sounds like a good place to start. Okay, 3 times 1 is 3. 3 minus 1 is a positive 2. So the minus goes with the 1. That makes the 3 positive. Okay, so we know something is happening at negative 3. We know something is happening at positive 1. We just don't know what. We don't know if it's a whole or a vertical asymptote. We just know something is happening there. Now, the 2 in front, don't pull a 0 out of that. Okay, you need an x. If there was an x in front, you'd get a 0 or a something. But without an x, you can't get an excluded value. Excluded values come from groups with x's or lone x's. They don't come from lone numbers. Okay, things that times to 2 and subtract to what? Probably a 1. I bet there's a 1 in there. So 2 minus 1 is a positive 1, so that sounds like a good thing to go with. Okay, so that's a negative 2. The negative 1 turns into a positive 1, so we know something is happening at those values. So both functions have something happening at 1, but then they've got a different excluded value. So let's go look and see, and we'll look at A. A's already been taken, but we'll look and see what's happening. You know something's happening at negative 1 on A, and with the graphs, you know a little bit more than that. You know it's a hole. So we know there is a hole at negative 1. Okay, and we also know there's a vertical asymptote at 3. Now, like I said, A has already been taken, right? A was the very, very last equation we played with, so it's, we already claimed it, but that's kind of what you're looking for. So let's go down to B, because B has not yet been taken. Okay, so what have we got on B? So we're looking for holes and vertical asymptotes. We have a hole, and it's at 1. So you're looking at the x values on holes. You're also looking at x values on vertical asymptotes. So there's a vertical asymptote at negative 2. So we know something happens at 1 and something happens at negative 2. We have a match. We've actually just figured out the rest of it. So this guy, as I try and keep the pin from hitting the camera, is B. All right, and just to finish it off, let's go down and make sure we're right. It's always good to check your last choice. Something, a vertical asymptote, is happening at 1, and then something, another vertical asymptote, is happening at negative 3. So let's go confirm that our first equation matches. Yep, 1/2 horizontal, vertical asymptote at 1, vertical asymptote at negative 3. Now, we didn't know that that's what was happening in the function, but we did figure out that something is happening. So, yeah, we got it. All right, looks good. Okay, and that is how you play matching with functions and graphs. All right, for this part, the matching is done. But the first part of the worksheet, you have to differentiate between things like holes and vertical asymptotes. So just in case you need a little bit more examples or practice at that, we're going to go ahead and finish out all of these equations and break them down into what exactly they will have on a graph. Okay. So we know that this first one has a -3 and a 1. Those are excluded values. They're also called discontinuities. But what we don't know, unless you look at the graph we matched them with, is whether those are wholes or vertical asymptotes. That's where the numerator comes in. Okay, so we need to break it apart so that things multiply to 7 but add to 5. And that doesn't work. Things 7 and 1, that's all. And 7 and 1 do not add to 5. So you cannot factor the numerator, which means nothing is canceling. So both of those are vertical asymptotes. Okay, vertical asymptotes happen when you've got things in the denominator, they're related to x's, and they don't cancel. Plus we have the horizontal asymptote at 1/2. All right, so let's check out this next equation. Remember, we've already matched them with graphs, but again, this is if you need, a few more examples or would like to see a few more examples. Okay, things that times to 2 and add to 3. That does work. We're going to ignore the negative because that's not the link between the two. The link is addition, and that we can do. So things that times to 2, that's 2 times 1, and they do add to 3. Now here's the catch. They have to times to a positive 2, but add to a -3. Well, if they're timesing to a positive 2, they're the same sign. Well, that just means you give them the sign that they're adding to. So if they're adding to a -3, you make them both negative. And then -2 and -1 make -3 when you're adding. Okay, now looking at what may or may not cancel. X minus 2, x plus 2, those are conjugates, but conjugates don't cancel. Duplicates cancel. And that's where the x minus 1s come in. Those are duplicates, which means they are going to cancel. And that means that the 1 is a hole. Holes can be canceled. They're like little potholes. You can take them out of the road. You can pave over them. You can ignore them. Canyons are a little harder to ignore. Okay, so we've got a vertical asymptote. That's an up and down infinity. The hole is a hole. Horizontal asymptote goes back and forth. That's end behavior. The graph levels off at a value or a height of 1/2. Y equals 1/2. All right, let's get the paper to slide. There we go. Okay, from now on, and also including 7.6, if something says, hey, I'm a slant asymptote, it's not enough for you to just say, oh, it's a slant asymptote, that's great. You have to figure out what the equation is. Kind of like you can't just say, oh, it's a horizontal asymptote. You have to say, oh, it's 0, it's 1/2. You can't just say, oh, it's a slant asymptote. Okay, so we're going to set up a division problem, and there's a 0 placeholder at the back. Okay, 3x squared minus 12, I'm going to put that out here in the divisor spot without hitting the camera. It also has a 0 placeholder as a 0x, and you can certainly put that in. In fact, that might be even easier for you to do it, but I'm going to show you how to do it without. The divisor can go without its placeholder. Dividend is a little bit harder, but the divisor can do it. Okay, we need the x's to become x cubed, and we need to kill off that 3, which means we need the 1/3, and then that will cancel with the 3. So you need its multiplicative inverse, its reciprocal. Okay, and then to get an x squared to an x cubed, you just need another x. A 3 on the bottom is basically a dividing 3. Okay, so it's going to distribute. So it's also going to hit that minus 12. Okay, and here's where if you haven't, so I'm going to call it, it's -4x, but I'm going to put it in the wrong spot. This is where it's really, really important to match it with like terms, okay? So there's an x squared, but because we didn't put in our 0x placeholder, we didn't get the next term, okay? So what you do is you actually just kind of skip that spot because it would be a 0 anyway. So because it's a 0 anyway, it's still the -x squared and the dividend in the box, you still use it. But so it's going to come down, but yeah, that's going to be a 0 anyway. So if you forget the 0 on your divisor, you can live without it actually. Okay, keep in mind you are subtracting everything, including the 0, which really doesn't matter. Okay, we're going to bring down the 0, which again really doesn't matter. That's okay. Okay, we need 3x squared to become negative x squared. The x squared part's easy, so all we really need is to create that to be a negative 1, and we have to cancel it out again, so it's got to be a 1/3. Okay, we just put it over the last place. We got the constant. We could keep going, except that anything else we come up with is going to be a remainder, and we don't need remainders when talking about this. So that is the slant asymptote. Okay, so starting with 7.6 and continuing into 7.7, you are now required to say what the slant asymptote is, what the linear equation is. Okay? All right, so let's talk about vertical asymptotes and holes. So finding a greatest common factor is always a good place to start, and the denominator has a 3 that you can pull out of everything. So that would make it x squared minus 4. On top, you can pull an x out of everything as well. So that'll be x squared minus x minus 12. Okay. The x squareds in the parentheses are clues that you might be able to take that a little bit further, and especially if we're going to look for anything that cancels. Okay, so we're going to bring it down. I'm going to do the top first. So we've got that random x out in front. Okay, and the top doesn't, when you're breaking it apart, it doesn't tell us anything other than whether something cancels or not. So none of the vertical asymptotes or holes come out of the top. Okay, so we need things that times to 12, but they need to subtract to an invisible 1, which I filled in, so it's not invisible anymore. So they're subtracting to a 1. Well, 3 and 4 times to 12, and they subtract to 1. So we will fill those in. Okay, and looks like we're subtracting to a negative 1, so we probably want 3 minus 4. So 4 gets the negative, that means 3 gets the positive, and then they times to a negative 12. Okay, that's the numerator. The numerator is less important. The denominator is the key to these excluded values. X squared minus 4 comes from a conjugate. Those are difference of squares. Everything in there is a perfect square, and it's subtracting. So that's where you get your plus minus 2. So you get the conjugates that it's just xx and 2 times 2, and then you get back to x squared minus 4. Okay. Out of the parentheses comes a negative 2 and a positive 2. Nothing comes from the 3 in the front because there's no x in the front. It has to come from an x. Okay, and as for canceling, nothing's canceling. So those are both vertical asymptotes. And you can check this with the graph that, I think D was the graph we found. Yeah, so you can check and say, oh yeah, there they are. Okay, last one. Up top, if your lead x is negative, even if it's got a number in front of it, and this number can be factored out too, pull a negative. Just it makes life easier. So pulling a negative is going to get us x plus 1 in there. Okay, because the negative, remember, you have to be able to distribute back to the original value. Okay, so we haven't changed it, we've just put it in an equivalent form. On the bottom, we need things that multiply to 3, but then they subtract to a 2. Well, 3 and 1 multiply to 3. They also subtract to 2, so those are good. They're subtracting this time to a negative 2. So that probably means we want 1 minus 3. So we're gonna, the 1 gets the positive, the 3 gets the negative. We are now looking for excluded values. So we get a positive 3, a negative 1. These are also known as discontinuities. And now we have to figure out, well, what kind are they? Well, the one part of it is canceling, so that's a hole, because you can pave over holes. You can cancel out potholes. The 3, not so much. The 3 doesn't cancel. So that is a vertical asymptote. Okay, and so that finishes it off if you needed a few more examples of how to do all of it put together all at once.